Fermi Paradox is just, where are the aliens? If the universe is really 13.8 billion years old, shouldn't there be aliens everywhere? And if not, why not?
The human brain is an incredible machine, one of the most advanced on Earth. But even with all that brain power, there are some ideas that just don't compute. One of the biggest mental roadblocks? Paradoxes. You see, our minds are wired to make sense of the world in a certain way. We expect logic, cause and effect, straightforward answers. But paradoxes throw all that out the window. They challenge what we think we know about reality and hint that the universe might play by very different rules. And right now, physicists might have cracked a paradox that's stumped scientists for over 50 years. But have they really solved it? And what about the other paradoxes that continue to baffle even the brightest minds? Let's dig into one of the most famous, the Fermi Paradox. You've probably heard of it. It's named after Enrico Fermi, the Italian physicist best known for building the first nuclear reactor. One day, Fermi asked a deceptively simple question. If the universe is so big and so old and full of stars like our sun, where is everybody? Where are the aliens? That's the heart of the paradox. Our solar system is relatively young. Other stars have been around for billions of years. Longer, plenty of time for intelligent civilizations to evolve and master space travel. So why haven't we seen any signs of them? Some skeptics say, well, maybe it's not a real paradox. We don't even know if intelligent life exists out there, but that's where the Drake equation comes in. It's a mathematical formula that tries to estimate the number of alien civilizations in our galaxy we might actually detect. It factors in things like star formation rates, how many planets could support life, and how long civilizations might send out signals. Back in 1961, when the equation was first introduced, we didn't know of any planets beyond our solar system. Everything was based on speculation. But that changed big time. Fast forward to 2020, using data from NASA's Kepler Space Telescope, astronomers made a stunning discovery. There are over 300 million planets in the Milky Way with conditions similar to Earth. That means rocky worlds orbiting sun-like stars, sitting right in the Goldilocks zone where liquid water could exist. Not too hot, not too cold, just right for life. Here's what's even wilder. Planets are more common than stars. Let that sink in. For every star you see in the night sky, there could be multiple planets circling around it. And we're not done yet. Very soon, the James Webb Space Telescope is heading deeper into space. Its mission? To scan those distant worlds and search for the building blocks of life, or maybe even signs of life itself. So yeah, things are about to get really interesting. Make sure you stick around. We've got a whole video coming up on the James Webb Telescope and what it could mean for the search for life beyond Earth. You won't want to miss it. Now that we know just how many Earth-like planets are out there and how many chances there are for intelligent life, the big question still remains. Why is the universe so quiet? With all these possibilities, why haven't we heard anything? Or have we? As our technology gets more advanced, we might be getting closer to an answer. Or maybe we've already been visited and we just didn't recognize it. Mysterious UFO sightings have been piling up in recent years, and some people believe aliens are already among us, quietly observing. If we ever found hard proof of that, game over. The Fermi Paradox solved. But until then, let's take a turn into something even weirder: time travel. Yeah, we're going there. Let's start with something called the Bootstrap Paradox. It's one of those mind-bending time travel problems that sci-fi writers love. You've probably seen it in shows and movies like Doctor Who, Terminator, or even Bill and Ted's Excellent Adventure. But here's the twist. It's not just fiction. It's a real philosophical headache for physicists and thinkers alike. So, let's break it down with a fun example. Imagine you're a time traveler. Before you take off, you stop by a bookstore and grab a copy of Shakespeare's Hamlet. Then, you zip back in time, way back to Elizabethan England. You meet a young William Shakespeare and hand him the book. He reads it, copies it word for word, and publishes it as his own masterpiece. Fast forward a few hundred years, Hamlet becomes world famous, printed again and again, and eventually one of those copies ends up in the exact same bookstore where you found it. Now here's the paradox. Who actually wrote Hamlet? It wasn't you. You just passed the book along. And it wasn't Shakespeare, because he got it from you. The book exists in a never-ending time loop with no real origin. Wild, right? But it gets even crazier. Ever heard of the Grandfather Paradox? Let's say, just as a thought experiment, you travel back in time and prevent your grandfather from ever meeting your grandmother. We know you love your grandparents, don't worry, this is just hypothetical. If your grandfather never existed, that means your parent was never born, and that means you were never born, which raises a terrifying question. If you don't exist, how could you go back in time to change history in the first place? Boom. The logic breaks. Everything unravels. You've basically deleted yourself from existence, and if that happens, then the timeline where you took that trip can't exist either. So, what would happen? Some scientists think this would create a new timeline, a sort of alternate reality, or even a parallel universe. You wouldn't be erasing your own timeline, you'd just be branching off into another one. You hop in your shiny time machine, jump to the 1930s, and take action before the war ever happens. But here's the kicker. If you succeed and the war never takes place, then there's no reason for anyone, including you, to go back in time in the first place, which means the event that caused you to act never existed, which means you didn't act, which means the war does happen. Welcome to the maddening logic loop of time travel paradoxes. So, whether we're looking up at the stars and wondering why no one's calling, or questioning whether you could actually high-five your past self without breaking the universe, paradoxes are here to mess with your head. And we've only scratched the surface. Stick around, we've got more time-bending, universe-warping content coming your way. Trying to play time-traveling hitman? Yeah, that's where things get really messy. The moment you go back in time to eliminate someone, say Hitler, you're not just rewriting history, you're creating a full-blown paradox. According to the many worlds theory, doing something that drastic wouldn't change your original timeline. Instead, it would branch off a new one, where Hitler never came to power. But here's the catch. The original timeline, with all its history, still exists. You've just added a new version to the cosmic playlist. And here's the kicker. That new timeline? It might not be better. In fact, it could be worse. But what if, instead of going back in time yourself, you sent something else like an object through time? Enter wormholes. Now this brings us to one of the coolest time paradoxes ever proposed by none other than the legendary physicist Joseph Polchinski. He's the same guy who literally wrote the book on string theory, but he also cooked up a wild thought experiment involving a billiard ball. Here's the setup. Imagine firing a billiard ball into a wormhole. If you shoot it just right, it exits the other end of the wormhole in the past at the perfect angle to smack into its earlier self. The impact knocks it off course, preventing it from entering the wormhole to begin with. But if it never enters the wormhole, how did it travel back to hit itself? That's the paradox. But wait, it gets weirder. Some clever physics students worked out a loophole, pun intended. Instead of the ball hitting itself head-on and stopping its journey, it could come out at just the right angle to give its earlier self a light nudges, a glancing blow. That small bump changes the trajectory just enough to ensure the ball still enters the wormhole at the same angle needed to deliver that same bump. And just like that, the loop closes without breaking reality. It's a perfect time, twisting dance. No contradictions, just weird, beautiful physics. But if you think that's mind-bending, get ready for the observer effect in quantum mechanics. This one will really mess with your head, and it all goes back to a thought experiment you've probably heard of. Schrödinger's cat. Important side note, no actual cats were harmed in this example, it's purely hypothetical. Here's the idea. A cat is placed in a sealed, windowless box. Inside the box is a bit of radioactive material, a Geiger counter, a hammer, and a vial of poison. If the material decays, and there's a 50% chance it does, it sets off the Geiger counter, which then triggers the hammer to smash the poison vial, killing the cat. But here's the twist. Until you open the box to observe what happened, quantum physics says the cat is in a strange superposition, both alive and dead at the same time. It's not that we don't know which it is, it's that until someone observes it, reality hasn't decided yet. This is the observer's paradox. The very act of watching something can change what's real. Reality, at the quantum level, seems to depend on whether we're paying attention. So, between alternate timelines, billiard balls fighting themselves, and cats living in limbo, one thing's clear. The universe is way stranger than we ever imagined. And we're just scratching the surface. So how can just looking at something change what it does? Sounds crazy, right? But in the quantum world, it's not just possible, it's how things actually work. In fact, the mere act of observing something can change its behavior. Reality, it seems, isn't fully real until someone watches it. Still wrapping your head around that? Let's dive into one of the most famous experiments in all of physics, the Double-Slit Experiment. This one will really challenge what you think you know about the universe. Picture this. You've got a wall with two narrow slits in it. Now imagine you're tossing tennis balls at that wall. Some bounce off. Some go through the slits. Behind it is another wall where the balls that make it through will hit and leave a mark. Easy enough, right? You'd expect to see two clusters of marks, one behind each slit. That's exactly what classical physics would predict. But now let's swap out tennis balls for something much smaller: photons, tiny particles of light. Here's where things get weird. When you shoot individual photons, one at a time, through those slits without observing them, they don't just hit two spots. They form a full interference pattern on the back wall, like a wave that's gone through both slits at once and interfered with itself. Wait, what? How does a single particle go through both slits? That's the quantum mystery.
But here's the real mind-bender.
The moment you try to watch or measure which slit the photon actually went through, the interference pattern disappears completely. Instead of acting like a wave, the photon picks a side and behaves like a regular old particle. It's as if the photon somehow knows it's being watched and changes its behavior on the spot. Even wilder, this change seems to ripple backward, affecting what's already happened. It's like looking at the photon rewrites its history. How is that even possible? We still don't know. No one has cracked it yet. Maybe you'll be the one who finally solves it. But if you think that's the strangest paradox in physics, hang on, there's more. Let's talk about the black hole information paradox. One of the biggest mysteries in all of science. Here's the setup. When something falls into a black hole, it's gone. At least, that's what general relativity says. Everything, matter, energy, information, is swallowed and erased. But there's a huge problem with that. Quantum mechanics says information can never be destroyed, ever. So which is it? Let's say you write two totally different letters on two pieces of paper. Then you burn both letters. The paper's gone, but technically, all the information about the ink, the handwriting, the paper's structure is still floating around in the smoke and ash, at least in theory. Now imagine tossing those letters into a black hole instead. According to classical physics, they vanish forever. But quantum theory says that's impossible. something about them should survive. So where did the information go? That's the paradox. And solving it isn't just a cool thought experiment, it could be the key to uniting quantum mechanics and general relativity, two of the biggest ideas in physics that still don't quite play nicely together. So yeah, the universe is full of paradoxes, and every time we think we understand it, it throws us another curveball. Maybe the truth is waiting just behind the next observation. Sure, turning ashes back into paper might sound impossible, but technically, it's not. If you had incredibly precise tools, you could measure tiny differences in the heat, the chemical makeup of the smoke, and the leftover ash to figure out what was originally written. The information is still there, just scrambled beyond recognition. Now here's the catch with black holes. They don't leave behind smoke or ashes. When a black hole devours something, whether it's a star, a spaceship, or a letter, it eventually starts giving off Hawking radiation, a faint glow, named after the legendary physicist Stephen Hawking. But here's the frustrating part. That radiation, it's completely generic. It doesn't carry any fingerprints from whatever the black hole swallowed, so unlike fire, which at least leaves clues, black holes seem to erase everything. And
This is where things get exciting.
A new wave of physicists now believes that information does escape black holes, just not in the way we expected. The key may lie inside the event horizon in a mysterious boundary called the quantum extremal surface. Think of it as an invisible layer within the black hole that's quietly tracking what's going in and what's eventually coming back out. As the black hole shrinks over time and radiates energy, this surface appears to encode the information being released, almost like it's keeping a cosmic receipt. If this theory is right, then information isn't truly lost, it's just hidden in the radiation, too subtle for us to read, yet. We're still piecing this puzzle together, and it's far from solved. But each new discovery brings us closer to one of the biggest breakthroughs in physics, finally uniting gravity, quantum mechanics, and the true nature of reality. And when we crack it for good, you can bet we'll be here to break it down for you. Stay curious and stay tuned.